Hello everyone and welcome to the Engineering Mathematics course. This is Safa and in this video we are going to start with one of the most fundamental concepts in mathematics, functions. Functions are everywhere in engineering. We use them to describe voltage as a function of time, position as a function of time, temperature as a function of position, and many other relationships between physical quantities. So, before we move on to limits, derivatives, integration, and differential equations, we need to understand functions really well. In this lesson, we'll learn what a function is, how to identify its domain and range, how to work with different types of function, and finally, how to understand and interpret their graphs. So let's get started. By the end of this lesson, you should be comfortable with 6 important ideas. First, we'll define what a function actually is. Second, we'll learn about domain and range. Third, we'll look at some common types of functions that appear frequently in engineering. Fourth, we'll learn how function notation works. Fifth, we'll learn how to read and interpret graphs. And finally, we'll connect these ideas to some simple engineering examples. Let's begin with the most basic question. What exactly is a function? A function is a mathematical relationship between an input and an output. We usually represent a function using the notation y equals f of x. Here, x represents the input and y represents the output. The most important rule is this. Each input must correspond to exactly one output. For example, suppose we have the function f of x equals x squared. If our input is 2, the output is 4. If our input is 3, the output is 9. So the function takes an input, performs a mathematical operation, and produces an output. You can think of a function like a mathematical machine. You put something into the machine and the machine produces one specific output. Let's make this idea more concrete. Consider the function f of x equals 2x plus 1. We can think of this function as a machine. The input is x. The machine multiplies the input by 2 and then adds 1. Now let's say our input is 3. We substitute 3 for x. So, f of 3 equals 2 times 3 plus 1. This gives us 7. Therefore, when the input is 3, the output is 7. This simple idea will appear throughout this entire course. We will constantly define a quantity as a function of another quantity. Okay, now let's look more carefully at function notation. When we write y equals f of x, x is usually called the independent variable. The value of y depends on x, so y is called the dependent variable. And f represent the function itself. For example, suppose we have f of x equals x squared plus 3x minus 2. The equation tells us exactly how the output changes when the input changes. We can calculate the value of the function for any valid value of x. Let's try one. If x equals 2, then f of 2 is 4 plus 6 minus 2, which gives us 8. So the function maps the input 2 to the output 8. Now we come to one of the most important concepts, domain. The domain of a function is the set of all input values that are allowed. In other words, we ask which values of x can we actually put into the function. Consider the function 1 over x. We know the division by 0 is undefined. Therefore, x cannot be 0. Every other real value is allowed, so the domain is all real numbers except 0. In interval notation, we can write this as negative infinity to 0, union 0 to infinity. Whenever you see a function, one of the first questions you should ask is, what values are allowed? The second important concept is range. While the domain tells us which input values are allowed, the range tells us which output values the function can produce. Consider f of x equals x squared. We can put any real number into this function. So the domain is all real numbers, but the output can never be negative. Squaring a real number always produces a value greater than or equal to 0. Therefore, the range is 0 to infinity, including 0. So remember, domain is about input, range is about output. Let's solve an example. Consider the function f of x equals the square root of x minus 2. We want to find its domain and range. Let's start with the domain. For a square root function, the expression inside the square root must be greater than or equal to 0. Therefore, x minus 2 must be greater than or equal to 0. So, x must be greater than or equal to 2. Therefore, the domain is from 2 to infinity. Now, let's think about the range. The smallest possible value inside the square root is 0. The square root of 0 is 0. As x becomes larger, the output increases. Therefore, the range is also from 0 to infinity. So, our final answer is domain 2 to infinity, range is 0 to infinity. There are many different types of function, but some appear much more frequently in engineering than others. Linear functions are used to describe simple proportional relationship. Polynomial functions appear in mathematical modeling and approximation. Rational functions are common in engineering systems and transfer functions. Exponential functions appear in growth, decay, circuits, and dynamic systems. Logarithmic functions appear in areas such as signal processing and measurement. And trigonometric functions are fundamental in electrical engineering, mechanics, wave, vibration, and signal processing. We don't need to study all of this in detail right now. For this lesson, our goal is simply to recognize them and understand their basic behavior. Let's start with the linear function. A linear function can be written as f of x equals mx plus b. Here, m represents the slope and b represents the y-intercept. For example, consider f of x equals 2x plus 1. The slope is 2 and the y-intercept is 1. Linear relationships are extremely important in engineering because many systems can be approximated as linear over a certain operating range. We will return to linear functions many times throughout this course. Okay, a polynomial function consists of powers of x multiplied by constants and added together. A general polynomial can have terms such as x squared, x cubed, and higher power. For example, x cubed minus 2x squared plus x plus 4. Polynomial functions are important because they can be used to approximate much more complicated relationships. Later, when we study Taylor series, you'll see how complicated functions can be approximated using polynomials. Another important family is exponential functions. A common engineering form is a time e to the power kx. Exponential behavior appear frequently in engineering. For example, the charging and discharging of capacitor, population models, system responses, and many dynamic processes involve exponential function. And our logarithmic function are closely related to exponential function. The natural logarithm, written as a ln of x, is especially important when solving exponential equations and differential equations. We will use both exponential and logarithmic functions later in this course. Trigonometric functions are particularly important in engineering. The three functions you will encounter most often are sine, cosine, and tangent. Sine and cosine functions are especially important when dealing with periodic behavior. For example, alternating voltage in an electrical circuit can be modeled using a sinusoidal function. Mechanical vibration can also be represented using sine and cosine functions. And signals, wave, and rotational motion all make extensive use of trigonometric functions. So, whenever you see a sine or cosine function, you should immediately think about periodic behavior. One of the best ways to understand a function is to visualize it using a graph. A graph shows us how the output changes as the input changes. Instead of looking only at an equation, we can see the behavior of the function. When looking at a graph, there are several important questions we can ask. Where is the function increasing? Where is it decreasing? Does it cross the x-axis? Does it have a maximum or minimum? And what happens to the function as x becomes very large or very small? These are questions will become extremely important when we study limits and derivatives. Okay, let's connect everything we've learned to a simple engineering example. Suppose the position of an object is described by the function x of t equals 2t plus 5. Here, t is the time and x represent position. At time 0, the position is 5. At time 3, we substitute 3 for t. 2 times 3 plus 5 gives us 11. So, after 3 units of time, the object position is 11. Notice something important here. We are treating position as a function of time. This is one of the most common ideas in engineering. Instead of simply saying that an object has a position, we describe exactly how its position changes with time. Let's summarize what we learned in this lesson. First, a function describes a relationship between an input and an output. Second, the domain represents all allowed input values. Third, the range represents all possible output values. We also looked at several common types of functions, including linear, polynomial, exponential, logarithmic, and trigonometric functions. And finally, we saw how function can describe real engineering quantities such as a position and time. This concept may seem simple, but they are extremely important. Everything we do later in this course will build on this foundation. Before we move on to calculus, we need to make sure our mathematical foundation is strong. In the next lesson, we'll review some of the essential algebraic concepts that we will use throughout this course. We'll work with algebraic equation, powers, roots, and other important mathematical tools that are frequently used in engineering. This concept may seem familiar, but having a strong foundation in algebra will make the more advanced topics in this course much easier to understand. So, in the next lesson, we'll strengthen our algebra skills before moving forward to limit, derivative, and integration. Thank you for watching. This is Safa, and I see you in the next lesson.